so now is the point where I want to talk a little bit, just say a few words really actually about the integration with iterated integrals. So you know that there is a gazillion methods to compute Feynman integrals. And I will try to, or at least attempt to mention some of them a bit later. I wanted to connect with Johannes' lecture, where he already introduced iterated integrals and polylogarithms. And I want to show how you can sometimes use them to compute Feynman integrals. So what is the point? So remember from Johannes' lecture, he introduced these functions that were written G, A1 up to AR, Z. So how were these defined? These were defined as iterated integrals. So the idea was that you have an integral from 0 to the variable that you specify. And I hope I do it right, that the last integration you do is a 1. I hope I copied this correctly. So you integrate, the first letter gives you the denominator of the integration, and then the integrand that you put in here is the remaining g's where you forget the first letter. And this thing itself is integrated only to the integration variable in the outer integration. So if you expand this recursively, what you get in the end is really an iterated integral. So you start out from 0 to z. You have dt1 over t1 minus a1. And then if you expand this, you get an integral from 0 to t1 dt2 over t2, sorry, a1, right? Please call me out when I make mistakes here. Yeah. A2, and then you have another integration 2t2 from dt3 over t3 minus a3, and so on. And then the last integration goes to tr minus 1 dtr tr minus ar. Thank you. Very good. And then these functions have different names, so they're called, so I like to call them hyperlogarithms. They're also called Goncharov. So this notation is certainly due to Goncharov. Goncharov polylogarithms. And you can also just think of them as multiple polylogarithms. So usually you define multiple polylogs in terms of the sum, but you can translate the two into each other. So they're really all just phrases to talk about the same type of functions. And now what you notice about these functions is, well, it's a nice definition maybe, but the point is that you're just giving a name to the integral of something that you already know with a denominator that is a linear function. So it is clear from this perspective immediately that you can write the triangle integral in terms of these g functions. Because in the beginning everything is linear, so you can do the first integral in terms of logarithms, which you can write as g's. And then the next integration, you have some denominator in front of the logarithm. But if you factorize the roots of this polynomial, you can always write it as a linear combination of these type of things, and it's a dilogarithm, right? The advantage of this notation is that once you have written your function in this form of the g's, it's very easy to derive expansions. You can compute the differential equations, because differentiating is easy, right? What is the differential with respect to z? Well, z is the integration boundary, right? So you just forget about the last integration. It's a bit more tricky when you take a derivative with respect to one of the other variables, but even that can be worked out. So you can do these things. You can compute functional equations. So this is just a very useful set of functions that has been studied very well, and for which you have algorithms to do manipulations. And now, if you want to apply this for Feynman integrals, there is a very special class of Feynman integrals where this is immediately useful. So you say, make a definition. Suppose that there exists an order, so a permutation of the parameters of your integration variables, x1 up to xn, such that all the lambda varieties or their corresponding polynomials, yeah, so say sigma 1 is the first integration, and say suppose you do the first k integrations, then you can compute this reduction with some improvements. And if the singularities after k integrations are all linear in the next integration, then you can apply the Goncharov polylogs to write down the integral, right? So suppose that for each k, after k integrations, all of these polynomials are linear in the next one. Right. So if this is the case, then we call the integrand we call it linearly reducible. And what I try to motivate by my few comments over here is that there are algorithms such that whenever you have a linearly reducible integrand, you can symbolically integrate it in terms of hyperlogarithms. So essentially the calculation at the end of last lecture was just an example of how you do this. And you can generalize all of the steps that we did last time to arbitrary weight Goncharov polylogs. The only condition is that, well, it's a very strong condition, but as long as you can factorize things linearly, then you can compute these things algorithmically. This is just a sufficient criterion. This is important to keep in mind. Because remember, this is just one particular integral representation. You may find a completely different integral representation in different coordinates, which may be much better behaved. So it is important here to note that often the thing may not be linearly reducible in the Schwinger parameters, but it may be linearly reducible in other parameters. Often better integral representations exists. Or are needed. So what I'm saying is that if it's not linearly reducible, it might still be a hyperlogarithm. It just may be the case that you have to be more clever in order to derive a better integral representation, which can be incredibly hard. And in general, I think to this day we don't have a general algorithm to decide whether a given integrand is a hyperlogarithm or not. I mean, in principle, integrates to a hyperlogarithm or not. In principle, you could look at the differential equation and factorize it, but also this can be very hard for very big systems. So in challenging situations, this is still not a completely solved problem to decide this question, whether a function can be expressed in this form or not.
Question.
Yes, sorry.
If the period is not multiple zeta value,
yes.
then is that like proving that this won't work at all?
I mean, this is for all polylogarithms, right? So if it's another polylog but not a zeta value, it could still be doable.
Yeah, but if the period is not a multiple zeta value.
If the period is not a polylogarithm at a special algebraic value, then it cannot be reducible. Indeed. So the really surprising thing is the other way around. When you have something that's horrible, you can combine elliptic integrals to get pi. There is a Legendre relation, right? So this is a very tricky game. But this is exactly why these period things are always just conjectures, because you don't have general algorithms to prove that no transformation exists of a certain type. Well, any questions towards this? Because we're very close to the end. So I just wanted to demonstrate how this can work. So I'm aware of at least 3 programs that you can use that do this. So there's software. There's a program called MPL by Christian Bogner. It's very aptly named. There is a very recent publication called Polylog Tools, I think, by Dulat, by Dur and Dulat. So you just, if you search for the name and the title, you will find it. So this is Maple. This is Mathematica. And then I have my own program for this. It's called HyperIn. And the intention was not because it's hyper good or whatever, it's because it's hyperlogarithms. This is also in Maple. Why not? I get this question all the time. I don't understand the question. Both of them are proprietary software systems. No, why Maple? The answer is it's the first one I ever used. To this day, I don't know how to operate Mathematica. But if you ask Jake, I think he has a Mathematica wrapper for the program.
It's actually just called Maple.
Well, but if people are happy wanting to have the interface.
Deep down, actually, HyperInt, we've thought a lot about rewriting HyperInt in Mathematica, and the biggest obstruction to this is that Maple is dramatically better at field extensions.
Oh, I always thought field extensions is the weak point of HyperInt.
Well, it's worse than Mathematica.
Okay. So let's go to this. Of course, you can always make things more complicated. So I would just want to illustrate how you would do the calculation from yesterday in this program, and I think it's going to be very similar in the other programs. Can you read this? Is this big enough? I can try to make it bigger, but I did find a zoom option earlier, but
Zoom factor.
is it here?
Yes.
Yes. Is this big enough? Okay, let's try to use this. So this is a package which you can download. You can find it on Bitbucket. There's a repository. You can just download the executable, the file. It's a text file, so you can mess with the code if you want. Not encouraged. So here, this is the calculation of the example. So I just defined the 2 graph polynomials. And then because Maple already has an integration command, the integration command of this package is called HyperIn. So the integrand for the leading order was just UF, and then the second parameter is the variables you want to integrate out. So x1 and x2. And then you do this, you get this big mess. And normally you never want to look at this big mess. And what is the reason for the big mess? The big mess comes about because, as we also saw yesterday, there's a million ways to write down a polylogarithm. There's all these functional equations. Remember, we had equations last time like d2 of 1 minus z is something like beta of 2 minus d2 of z, something else, and stuff like that. So there's always a problem when you're dealing with these expressions that there's no canonical way to write them down. And what this program does, it uses some way that is convenient for the integration, but that's maybe not very useful. So what you do afterwards is you try to bring it into a canonical form, and that's called a fibration basis. And maybe this is worth mentioning because this is very useful in manipulating these kind of expressions. So what is this Li I2 of 1 minus z? If you write it as a Gonchar of polylog, right? So you would write it as g of, I think there's a minus, my notation 0, 1. So this is the dilogarithm. And then the argument is 1 minus z. This is nice. But now on the right-hand side, you have written it as something with Li2 of z. So here, the Li2 of z is g of 1, 0, z. So what you have done in this functional equation is that you have forced the final argument to just be z. So this is one way to canonicalize the representation. So if you give me any polylog with weird arguments, you can always rewrite it such that the argument is just z. And all the complexity goes into the letters and maybe the constants. And once you've done this, the representation is unique. So this is a unique way to write it down such that only the final argument depends on the variable that you're interested in and the rest is independent of the variable. And that's called a fibration basis. Now, this would be the canonical answer, but the problem is if you have several variables, there's also not a unique fibration basis because you can do it in different orders. You could say, first, let's assume z bar is fixed, and let's try to put z in the final argument. Then z bar could still appear in the letters. And then the remaining function, which is only a function of z bar, you bring in this other form. But you could also do it the other way around, and then you will get different expressions. They can be very different in size. So there's a choice to be made, and Hyperint doesn't attempt to make a choice by itself. So you just have to tell it. So I'm telling it to take this mess of an expression, bring it in a fibration basis, where first we want to move z into the argument, and everything that's left over, I want to put z bar in the argument. So this is what this command does. And then you get this expression, which already looks a bit shorter. So you see we have this z minus z bar denominator, which is exactly what we expected. And this h log is exactly how Hyperint writes these g's. So just replace h log by g. This is just the Hyperint notation. And now you can convince yourself that this is the same expression that we did last time, just written in terms of contour of logs. Remember, we had terms which were products of log of z and log of 1 minus z, and if you use a shuffle to write it out, you get this type of expression. Now, the interesting point of this polynomial reduction business is that these considerations we had down here, that they are actually valid for arbitrary orders in epsilon, right? Because we only looked at the singularities. And that did already account for the possibility of logarithms. So what we can do, let's look at the next order in epsilon of this integral, right? So you would have log of, I think it was u squared, keyboard, u squared over f. I think that's the term next order in the epsilon expansion that we derived earlier. And then you know from the get-go, it does not change the polynomial reduction, right? You will get a function of the same type in the output. It gets a bit bigger. You get this kind of result. And now there's two things that you notice. So one is that the letters have become longer. So instead of just 2 integrations in these g functions, you now have 3 integrations. So this is what's called the weight. And the very naive idea is now you started with the logarithm in the integrand already. So you already had a weight 1 function. And you do 2 integrations, so now you get a weight 3 function. So with each order in epsilon, you should expect at least some parts of the answer to grow higher in weight. And the other thing you notice that now you have a term, if you look like at the second row from the bottom, there's this term here, where you have a contour of log of z where the z bar appears in one of the arguments. And this is the kind of term which would look different if you would move the z bar in the argument and the z out. Yeah, so this is the kind of expression that you get. And this is why this is actually not a single-valued multiple polylog anymore. So Johannes introduced last time these functions which are combinations of contour of logs at z and z bar, which have no monotomies. But they wanted to have letters 0 and 1. And then you can define single-valued MZVs. Now this is a slightly more general function because you have the z bar in the argument. But again, this is just another form of the singularity when z equals z bar. So it can also appear in a logarithm in this form. Well, and though you can keep going and compute any order that you like. Maybe just one thing. So if you have such an expression, and you want to rewrite it in the other order, so you can take this expression, and now you say, I want to move z bar into the argument first, and then z. What did I do? Oh yeah, this is good. It even gives you useful error messages. Isn't this amazing? So now you get an expression like this. And what does this mean? But this is an identity, right? It just rewrites this function contour of log of z with these 3 arguments in terms of other contour of logs. And you see that every term of this expression, when you have a z in the first argument, then you don't have a, and then you have a, yeah, so now you have z bars in the first, and the z can appear in the letters. Where is it? Yeah, there's one. So here's one, right, where now you have the z bar first and the z in the argument. And you also see that there's some imaginary parts popping up. So as you know, you have to be very careful when you deal with these polylogs, because in general, they have monodromies. When you move around 0 or 1 minus z, then they can pick up 2 pi i's times something. And an individual polylog will always have all sorts of branch cuts. So this is what happens in this rewriting process. These delta terms here just tells you that depending on whether the imaginary part is positive or negative, you get a plus I pi or a minus I pi. But if you transform the whole expression, which doesn't have monodromies, then all of these i's will disappear. So maybe just one more thing I want to show is the polynomial reduction that we did earlier. So let's say that the way this works is you set up a table which holds all of these singularities. And then you say, if you haven't integrated anything, so after the empty set, so I don't have an index in my S, then you just have the U and the F polynomial. And there's a weird reason that I won't explain why you do this funny thing in the other argument. And then you have a command that's called CG reduction. CG stands for compatibility graph. It's a slightly fancier version of what we did here. It still gives you an upper bound on the singularities. And here I'm also telling it that it should not attempt to integrate out z or z bar. We don't want to integrate those variables, right? So this is the only thing I'm specifying here. Then you get a calculation, and then it does the computation, and the final output is the remaining singularities. So you should only look at the first part of this. So it tells you that there's singularities at z equal 1, z bar equal 1, z equals z bar. The things with z and z bar itself going to 0 are not listed. So these are always assumed in this boundary, the trivial singularities when things get 0 or infinity. So it only shows you the other ones. So this is the singularity of the integrated function. And indeed, we've seen that the leading order and also the next order only had singularities in the set. And if you just want to see what are the singularities after the first integration, say, so this is what we computed earlier. Sorry, I called it differently. Then you get exactly the polynomials that we computed earlier. So there is well, that's exactly what we computed. Yeah. So you can take it out of the table. So if you want to check if something is linearly reducible or not, what you do is you take the polynomials, you throw them in this reduction, and then you can also just suggest integration order. And in this case, it doesn't matter because everything is linear, but in complicated cases, you have to be very smart on which order you integrate. And this will tell you how to do so. So this is, any questions about that? Then I just want to wrap up with a couple of comments of all the things that I didn't talk about. So things are pretty well, though still not to full satisfaction, understood in the case when you get polylogarithms. So when you have polylogarithms, you can also go by the differential equation, bring it into canonical form, and write down to all orders in epsilon the representations if you have integration constants, or use summation methods. There's very powerful summation technology. Yeah, I have a list of references. I just don't have the time to write it down, I think. But just in the grand scheme of things, there's also a more general classes of iterated integrals. So one of the approaches that we used here was that we used some simple building blocks, and then we just put them together by iteratively integrating. And if you think about solving a differential equation, this is what the Picard recursion is about. You solve the leading order of the differential operator, and then to each order in the expansion, you just have to integrate your right-hand side against the kernel. It's like the Feynman expansion. I mean, you always integrate over the Green's function one more time. So in a way, these d logs are the Green's functions for the first-order differential equations. Now, what happens if you have a second-order differential equation? Then you have to look at the homogeneous solutions of that and integrate with those as kernels. And this gives you iterated integrals of so there's more iterated integrals. So we've talked about polylogs. There's also elliptic. polylogarithms. You can look at, there have been examples of iterated integrals of modular forms. Even more general, just arbitrary second order differential equations. Yeah. Don't know how to write this down. So this is a big field of research to look at iterated integrals and classes of iterated integrals that you can still handle algorithmically, and trying to understand which Feynman integrals you can express in terms of them, developing algorithms to compute them. And so I have a long list of references for this. And maybe it's most useful if I email this around instead of copying a ton of archive numbers on the board. So I have a list of references about, so some references about things that I talked about. In particular, some introductory things. There's a textbook by Smirnov about Feynman integrals. There's lectures on differential equations, which I didn't talk about. And lectures on iterated integrals and quantum field theory and Feynman integrals. Computer algebra tools, summation methods, dimensional recurrences. So I will send around an email with this list of references if you're interested in. Otherwise, I thank you very much. It was a pleasure. And if you have any questions, then ask me now. And good luck with your research. Yes? Well, I mean, this depends on how the Feynman integral is defined. So, at least the way I understand it, the traditional way to define Feynman integrals is to do Wick rotation here in the Euclidean, and then you analytically continue back to the Minkowski. This you can do. I mean, now you have a polylog, and now suppose you want to send z to minus z. Well, that's a trivial thing. If you have an iterated integral, analytic continuation is the easiest thing to do. Maybe I should have mentioned this. Because what does iterated integral mean? You're integrating from somewhere, from some starting point to some other point. Now you want to integrate to some other point in the negative domain. Then there's a funny thing called a path concatenation formula, and then you can always write down the monodromy or the analytic continuation to whatever sheet you want to go at in terms of explicit terms, which are, again, just Goncharov polylogs evaluated at the branch points and things like that. So there is, so if you want to, so this analytic continuation, I think, is actually the easiest if you have any kind of iterated integral representation. So people have also used this for the iterated integrals of elliptic polylogs, modular forms. Also there, the analytic continuation is actually very convenient to do. I think if you want to compute the integral in the first place in the Minkowski, I mean, then the question is how is it defined? So by direct integration, I wouldn't know how to do it. But for example, if you use algebraic methods, like symbols, like ansatzes, or if you use differential equations, I mean, those don't change the form if you analytically continue because the coefficients are analytic. So you can do directly in the Minkowskian region, and then you can boil it down to the boundary values in the Minkowskian, which are then much easier to get. But I think for the purposes of direct integration, what you really want to do is to at least put a little epsilon to give a well-defined imaginary part to everything, and then you can do the symbolic integration. So I think all the programs, what they do is they treat the variables as generic, as not to be real or anything, because then you always run into problems. Also, when things are positive, there can be a fake singularity on the real axis, which you don't want to integrate over. But you just treat them symbolically, and then only when you evaluate them for special values, you will see some imaginary parts coming up on it. So I'm not saying it's trivial. Yeah, you have to be very careful that you trace all the invariants and which way they go around zero when you go to the Minkowskian, but it's doable. It's not the bottleneck, I would say. I think the important part is that there's no extra singularities in the regularization, right? So sometimes you could imagine if you put p squared equals minus m squared or whatever, or p squared equals m squared, right? Now you kill, as we discussed last time, the power counting can change. You can create poles and epsilon. So this is something you have to put in from the beginning, that you keep the right monomials. But then the actual value of the coefficients in the polynomials, those you can tune via analytic continuation, as you like.
So there will be an announcement in a second, but before that, I think we should give another big hand for this nice set of lectures.
Thank you.